Hello guys, welcome back to my channel. Today we'll be going through the introduction to optical fiber communication. In this video, we'll be covering the topics introduction to optical fiber communication and the advantage of optical fibers. We'll be going through the basic principles of optical fibers like total internal reflection, Snell's law. We'll go through another concept called acceptance angle, and we will show you the relationship between Snell's law and acceptance angle also. um, we will also introduce another topic called as numerical aperture and the relationship between, which is basically relationship between acceptance angle and a certain refractive index. We'll also go through the structure of an optical fiber. We will go through modes and number of modes. We will also in the end with the difference between a single and a multi-mode optical fiber. So before we begin, it would be really appreciated if you could subscribe to my channel and also like this video, as it will encourage me to make more videos like this. So let's begin. The introduction to optical fibers. As you can see, the proposals for this system of optical fibers via dielectric waveguides, or also known as optical fibers from glass, made from glass for example, was to avoid signal degradation, i.e. losing signal to the environment. This proposal was given by Cow and Hockham and Wirtz in the year 1966. This is a schematic diagram of an optical fiber where the information source transmits it electrically to an optical source. So hence here the conversion between electricity to optical energy happens, and then it enters the optical source, and then the optical source transmits it to the wire through the optical fiber cable, which takes it to the optical detector, and then there's a conversion here between optical to electrical signal, and then the electrical receiver receives the electrical signal and then sends it to the destination. So this is a basic schematic diagram of the system. Here we look at the advantages of optical fibers. Optical fibers are very small in size, very small. Hence, they're also very lightweight or less weight. They have extremely huge bandwidth, potential bandwidths. They have very good electrical isolation. They're almost electrically isolated. They have a very low transmission loss, which here is given as 0.2 decibels per kilometer, which here is very low transmission loss. Hence, it is immune to interference and crosstalk, which hence ensures signal security, that there is no degradation of signal going out into the environment and everything is retained. And lastly, it is very rugged, it is very flexible, and it's also very cheap, these optical fibers. Now we will go into one of the more important topics of this system, the principles of optical fibers. The basic principle of light propagation in an optical fiber is total internal reflection. Total internal reflection basically occurs when electromagnetic waves or light travels between an optically denser medium to an optically rarer medium. And we know that the refractive index is basically the ratio of speed of light in vacuum to the speed of light or speed of light in a given medium. So if the angle of incidence of the ray entering is greater than or equal to a certain angle called as the critical angle of the medium, only then does total internal reflection as a phenomenon occur. So the angle of incidence should be greater than or equal to the critical angle of the medium. Only then will TIR or total internal reflection occur. The expression for critical angle can be found through Snell's law. As we know, Snell's law is basically the relation n1 sine theta 1 is equal to n2 sine theta 2, where n1 is in general context is the refractive index of the rarer medium, and n2 is the refractive index of dense medium. and this theta 1 here would be the incidence angle, and this would be the refracted angle. And here we would see in the TIR context, N1 would be the refractive index of the denser medium, and N2 would be the refractive index of the rarer medium. And this phi c or theta c would be the critical angle of the medium. So hence sine phi c is equal to ratio of refractive index of rarer medium to refractive index of denser medium. So hence, as we saw in the previous slide, that any angle greater than or equal to critical angle, the angle of incidence should be greater than or equal to the critical angle, only then TIR will occur. So hence any imperfections in the core cladding interface, which we will see later, this being the core and this being the cladding, any imperfections in this interface, then there will only be regular refraction and hence TIR will not occur. Regular refraction being that the light will escape here out instead of reflecting completely. So there shouldn't be any imperfections for TIR to occur. This figure here would give you a simple representation of the core cladding interface and how TIR occurs in the core. Now we go into the next topic called as the acceptance angle. I would explain acceptance angle in a very easier way through this scale. Let's assume that this scale is the normal of the core, and then the rays entering at this angle. And if this, say for example, this is the maximum angle at which light can enter the core. So any angle lower than that or equal to that, only then the ray can enter the core. Any angle which is higher than this angle, like this for example, will not be allowed to enter the core. So let's see this through. So any rays with small grazing angle at the core cladding interface are only transmitted and then undergo TIR. So hence, obviously not all rays, as I showed you there, can enter the core cladding interface. So any angle greater than that certain maximum angle will not be allowed into the core cladding interface. When a ray of light of angle theta, a random angle theta, approaches the interface, it will enter the interface only if and only if theta, the angle, is lesser than or equal to the specific angle or that maximum angle that we set. The theta should be less than or equal to that specific angle known as the acceptance angle. But so if any angle theta is greater than the acceptance angle and lesser than the critical angle, sorry, any angle that is greater than the acceptance angle will not enter the interface, and any angle theta less than the critical angle will not undergo TIR. So the angle theta should be in the range that is theta should be less than theta c and should be greater than theta a. Sorry, it should be greater than theta a, sorry, theta c, and should be less than theta a. Now we go into the next topic known as the numerical aperture. Numerical aperture basically is the relationship between acceptance angle and the refractive indices of the core and the cladding. So here we see the n naught being the refractive index of the surroundings, theta 1 being here the acceptance angle or the angle of the incident ray that's trying to enter the core, theta 2 being this angle here, phi being the angle at which TIR could happen, for example. So here we see that this normal, since normals are always 90 degrees to the straight line here, so this is 90, we can say that phi is equal to pi by 2 minus theta by 2 or 90 minus theta by 2. So now through at this interface, for example, we can apply Snell's law. So when we apply Snell's law, we get the relation n naught sine theta 1 is equal to n1, which is this, sine theta 2. But we know theta 2 is equal, theta 2 when rearranged will give us pi by 2 minus phi. But we know sine pi by 2 minus phi is equal to cos phi. But then we can write cos phi as root of under root 1 minus sine square theta. But we also know that sine phi in the critical angle formula is n2 by n1. So we put n2 by n1 here. So n2 square minus by n1 square. Solve it. Then we get n1 square minus n2 square by n1 square whole under root. So n1 and n1 here gets cancelled. So we get root of n1 square minus n2 square. But here we know that theta 1 is basically the acceptance angle. So we write that as theta A, and n naught stays the same, n naught being the refractive index of the surroundings. So numerical aperture is equal to n naught sine theta A, which is equal to root of n1 square minus n2 square. So this is the relation of the numerical aperture. But we can also write numerical aperture in terms of a certain other quantity known as relative refractive index between the core and the cladding. So this relation can be written as, firstly, we know that delta is equal to, delta can be written as n1 square minus n2 square by 2 n1 square. But we can approximate this value as n1 minus n2 by n1 when delta is less than 1 or is very less than 1. So through this we can find numerical aperture equal to n1 into root of 2 delta. So this would be the second way in which you can represent Na. Now we go into the structure of optical fibers. We have broadly divided structure of optical fiber into 3 parts: the core, which is this yellow thing here, the cladding, this white one here, and the buffer, which is the blue part here in the figure, the buffer or the sheath. So let's go into the core. The core of the optical fiber is one of the most important parts of the optical fiber, as that's the place where firstly the light will enter and the light will get transmitted, and hence obviously known as it's the transmission area of the fiber where the signal is passing through the fiber. And the typical diameter of the core is between 50 to 500 micrometers, or 50 to 500 micrometers being 10 to the power minus 6 meters. So next we go into cladding, which is this white portion here. The cladding here obviously surrounds the core, and as we saw in the previous concepts, that the cladding has a lesser refractive index than the core to satisfy the TIR condition that we wanted. And it also defines the optical boundary of the fiber. So no light can exit the cladding. Any light can exit the core, but it can never exit the cladding. So hence it defines the optical boundary of the fiber. The third thing, the sheath or the buffer, as given here, is basically just a special coating on special plastic coating that provides shock resistance to the fiber. Its thickness ranges from 250 to 1000 micrometers in thickness. So now we go into the next concept, which is the number of modes. As we saw in the introduction, we saw that optical fibers are a dielectric waveguide. We know that light is a electromagnetic wave, so the energy in the fiber that's propagating is propagated through electric field and magnetic field. And obviously, if any EM wave is being propagated through electric field and magnetic field, it can be analyzed by the Maxwell's equations. And we know that, and Maxwell's equations has different sets of solutions called as modes. Modes are basically something that give an account of the allowed optical path that the light can take in the fiber. and we can determine the number of modes by the horizontal wave number. There are two types of fibers on the basis of number of modes, one being the single mode fiber and one being the multi-mode fiber. And here we can see the relation of the horizontal wave number, which is represented by V, which is equal to 2 pi A by lambda into Na, where A is given as the radius of the core and Na is given as the numerical aperture. Now we'll talk about the single mode fiber. The single mode fiber, as you can see here, the core of the single mode fiber is very narrow. Hence, since it's very narrow, there is not a lot of light that can enter the core. So hence the acceptance angle becomes very small. So, and when the acceptance angle becomes very small, the numerical aperture naturally becomes smaller. So because of this, we can also say that it only allows one mode of light to travel. And because of this, the amount of dispersion is very less. And so a single mode fiber is used for very large bandwidth transmissions and very high speed transmissions. So a very high speed or very large bandwidth transmissions. And now for the last part of this video, we go into the details of multi-mode fiber. A multi-mode fiber relatively has a wider core. As you can see here, the core is bigger as compared to the single mode, and the diameters are approximately 50 micrometers. As you can see, there are more than one mode of light traveling. There are two types of rays that travel in the core. One is the axial ray and one is the marginal ray. So as you can see here, it allows different modes to pass through together. Instead of a single mode, you have many types of modes that are going in a multi-mode fiber. And that's it for today's video. Hope you found this video informative, and hope you can like, share and subscribe and comment your thoughts on this video. I will be getting the next lecture out as soon as possible. So thank you very much.